I want to spend maybe 20 minutes telling you about two topics that has to do with dark matter, in particular light scalar dark matter. I have fairly large number of collaborators, but I want to highlight the ones who are here. In particular, Austin is here. Austin sitting in the back. Alberto is here, and Luca as well, and Sam. Okay, they are all here in this conference. And let me start by giving you kind of a very quick introduction on light scalar dark matter. In fact, before I do that, let me also emphasize for much of what I have to say, in fact, the scalar dark matter can be quite a bit heavier than what I'm suggesting here, which is very often called fuzzy dark matter, around 10 to the minus 22, maybe with 1 order of magnitude slack. It's called fuzzy because the Broglie wavelength is rather long. And once again, I want to emphasize for most of what I have to say in the rest of the talk, the mass can be quite a bit heavier, and it doesn't really matter a whole lot. So to give you that introduction, what one has in mind is really a scalar phi here, which is some sort of axion with a potential that is non-perturbatively generated, for example, by some sort of instanton effects. The scalar can be thought of as an angle, and as an angle, it has a periodicity, which is often called the axion decay constant. I call F here. And if you expand out that cosine, you can read off the mass term, which is like so here. So this is similar to the QCD axion, but for the numbers that I'm going to use here is not the QCD axion in particular.
Maybe easier. It's already on.
All right, sorry about that. You can hear me? In particular, this lambda will be a lot smaller than lambda QCD. So such particle, there are many candidates for them. You can read this nice paper by Sergey and collaborators on candidates in string theory. So one motivation for thinking about such a light particle as dark matter is because the dark matter abundance works out rather nicely. And the story, just very briefly, is if you draw a potential like so, with a scalar field value that has some primordial VEF that's of the order of the periodicity scale, capital F here. What happens is in the early universe, the scalar field is basically frozen by Hubble friction. As the Hubble friction drops until it reaches the mass scale of the particle, it starts to oscillate. And the oscillation is basically is damped by the expansion of the universe with smaller and smaller amplitude closer and closer to the minimum. If you work out that story without giving you any details, the dark matter abundance work out to be just about right. If you make the following assumptions, that this F is somewhere between Guth scale and Planck scale, and the mass is rather small. So this is one motivation for thinking about a scalar particle that's a rather small mass. The abundance work out nicely in a very simple setup. Now, because the oscillations, for the most part, is very close to the minimum, because of the expansion of the universe, for the most part, you can actually ignore this full cosine potential, including the self-interaction. You can just treat it as a free massive scalar, so the Klein-Gordon equation. If you take the non-relativistic limit, which is a very common thing to do, we are interested in particles that exist, for example, in the Milky Way halo, whose velocity dispersion is a few hundred kilometers per second, so it's non-relativistic. So it's convenient to take a non-relativistic limit. Following standard procedure, introduce a complex scalar psi. You basically factor out the main time dependence with frequency m, like so. So that psi, it still has time derivative, but it's rather small compared to m, basically. And in that limit, you can show the Klein-Gordon equation reduced to Schrödinger equation. And in the presence of gravity, there's a gravitational potential that is sourced by the abundance of this scalar itself. And this is all rather standard, so I'm going by fairly quickly. And let me just emphasize one thing. Despite the appearance of the Schrödinger equation, this system is a classical system. If you work out how many particles you have in the de Broglie volume, for example, in the Milky Way is a huge number. From that point of view, it's a classical system. So psi here, even though I'm going to call it the wave function from time to time, should be thought of as just a complex classical field. There is an alternative perspective on this system, basically this Schrödinger equation system, supplemented by Poisson's equation that sources gravity here, the gravitational potential. There's an alternative description in terms of a fluid, and that alternative description is to break the complex scalar as an amplitude and a phase. The amplitude can be interpreted as the square root of the density, and the phase can be as a velocity potential, so the velocity goes like the gradient of the phase. In that case, what is normally, you might be familiar with in quantum mechanics, probability conservation of the Schrödinger equation becomes mass conservation here. This is a complex equation, so there should be two independent equations. The other one is the following, somewhat weird-looking Euler equation. Most of the terms are familiar. This is the unfamiliar-looking term. This term is often called the quantum pressure, although it's a little bit of a misnomer to call it pressure. And in this context, it's also a misnomer to call it quantum, because it's really a classical system. Okay, so we'll come back to this way of thinking about the system in a minute. But let me emphasize one thing. This is a system where the fluid really behaves like a superfluid in the sense that there's no curl. The velocity is a gradient flow. And as I said earlier at the beginning, most of what I said, I have to say in the rest of the talk, the scalar could well be quite a bit more massive than the number given above. So let me start with the first topic, which has to do with, actually before I start with the first topic, let me just tell you there are many ways observationally to distinguish between fuzzy dark matter and more normal cold dark matter. By normal, you could just take the m go to infinity limit of what I said earlier. Anyways, I'm not going to go through them at all. Suffice to say, most of these ways to tell the two apart has to do with basically the wave nature of dark matter. In other words, the density, remember, the density is the density is psi square. And so if you have a superposition of waves in a halo, you are going to have interference effects. And a lot of these interference effects are very interesting. Perhaps it's just easiest to just show you in a picture. In a picture, if you start from cosmological initial conditions and just run with a simulation, numerical simulation, you will find basically a density plot like this. The color coding here is density. You will find distinct basically patterns of density that looks like interference fringes in a halo and also along filaments. Perhaps I have time to show you a movie of that sort. You can see this is not a movie in time. It's just taking one of this simulation at a fixed time and slicing along the z-axis. Okay, but you can see this interference of structure, and there are many implications of this. I'm going to tell you one implication and focus on, in particular, vortices. Okay, as one of the implications. And then the next topic I'll talk about is what happens if you combine this with the presence of a black hole. Okay, perhaps the first question you might ask is why even thinking about vortices? Remember, in the fluid picture, this is really a pure gradient flow. And as such, there should be no vorticity. And furthermore, if you look at the Euler equation, you can see the right-hand side is pure gradient. The gravity term and the quantum pressure terms. Pure gradient, it means that there is some form of Kelvins theorem, which tells you if initially you have no vorticity, which you don't have in cosmological initial conditions, you should not have vorticity at the end. So why even think about vorticity? Of course, the loophole in all these is the following. To even define the phase, better be true that rho is different from 0. The amplitude is 0. And as I showed you earlier, in the nonlinear regime, inevitably you have basically interference phenomenon, which means just by random chance, because of a superposition of waves, there are going to be destructive interference where actually rho goes to 0. And in those places, you have to worry about what actually does having a phase or not having a phase actually mean. And those turns out to be the location of what you might call topological defects, and vortex is one of them. Okay, so I'm going to tell you kind of a simple argument, not by starting with vortices, but by talking about walls. Okay, so let's do just one spatial dimension for now. So let's just imagine at some point the wave function goes to 0, right? Just by pure chance, destructive interference in a halo. So I can expand the wave function. This is 0. The first order term, let me assume, is non-zero. Okay? And remember, psi is a complex quantity, has imaginary and real part. And let me represent the gradient of psi at the location of the origin with this basically blue arrow, right? So imagine, again, you are in one spatial dimension. You are approaching the origin from the left and go to the right. What happens is psi would basically go from having this value, approach 0, and then go off in this direction. And if you think about the phase, it means the phase has a pi jump, basically going from here to there. It's a very simple argument. So this is the analog of a wall. So at the location of a vanishing density in one spatial dimension, you have no option. The phase has to jump. Yes? So that's the analog of a wall. And you can clearly generalize this to higher dimensions, basically like so, just putting arrow on top. Now, in higher dimensions, in particular in 3 dimensions, these places where the density or the wave function happens to vanish, it has to vanish for both the real and the imaginary part. And in 3 dimensions, if you ask yourself what is a surface of constant imaginary part psi, that would be a surface, right? And likewise, what is the surface of constant real part of psi, that will also be a surface. For both surfaces to match 0, they cross basically along a line. So in general, you should expect not a wall, but actually a line or string-like defect. Basically, it's a vortex. And you can convince yourself by looking at the phase, by going around, choosing a loop around basically this line defect. The phase has to wrap around by 2 pi. That would be basically for a wave function that goes like linear in separation from basically the point of the defect. Or if for some reason, by accident, this term is 0, you go to higher order, then you generate higher winding. Basically, this n here means you go to higher order. You are dominated by the higher order terms. Okay, you work out, for example, the circulation, the velocity integrated along the loop. You get basically integer winding loop. With u of h bar over m, h bar is set to 1 here. And there are certain generic things you can say. By this argument, for example, if your profile is indeed like this, remember rho is psi squared. So it tells you the density profile away from the defect goes like distance squared. You have to square this. If you have higher winding, then it will be r to the 2n. The velocity, on the other hand, remember, is just the gradient of the phase. So that always drops like 1 over r. Okay? Yeah?
The whole story started from the real scalar field.
Yes.
The equation of box phi.
Yes. Yes.
How can I see all of these vortices there? This is one question, and related to that confusion is that the way you introduce this psi is redundant because you have the scalar field, which is like the real part of psi.
Yes.
So there is some change in psi, which actually doesn't change phi.
Yes.
You have to keep track of that.
Yeah, what is important is if you think through what happens, is that by introducing the non-relativistic limit, somehow I generate a global symmetry. And the global symmetry is what? It's just a U1 for psi. And the global symmetry is very easy to understand. It's just particle number conservation. In the non-relativistic limits, you are not making these particles. You are not destroying them. You actually have a theory that if you want is some kind of emergent U1. And that's basically what we are taking advantage of here.
So what are the vortices in the phi, from the phi point of view? How can I see that there are this?
It's really because you are in the non-relativistic regime.
So they get destroyed
If you go to large velocity or go to the relativistic limit, you wouldn't have these vortices to think about.
Relativistic theory contains the non-relativistic one.
Yes.
Still be there.
But it's really because of the fact that you have this U1 that didn't exist in the relativistic theory, no? I mean that.
It's a field redefinition. It's non-invertible redefinition of real phi.
Well, you have to be a little bit careful. I'm not losing new degree of freedom or losing degree of freedom because this is a real scalar with second order 2-time derivatives. This is a complex scalar with 1-time derivative. So if you count the dynamical degree of freedom, I'm not introducing or.
The intermediate step of introducing going from a real to a complex field seems like cheap.
Yeah, we can discuss that. Perhaps maybe one way to answer your question is to ask, okay, this is the extreme non-relativistic limit. Suppose I want to ask, well, what is the small kind of relativistic correction, but sticking with the complex scalar? How would you write down that story? In fact, that story was actually recently worked out by and it's a little bit complicated, as you might expect, because the counting is complicated. Once again, because here you are going from a 2-time derivative to a single time derivative. But that's a way to do it. We can think about that. Yeah.
By particle pair production.
That's right. That's right. That's right. Yeah, we can discuss more. Thanks for the question. Okay. So there are vortices here with integer binding. Now the question remains, though. You might wonder. Okay, this is all nice arguments, but it's all predicated upon assuming that in an actual cosmology, these places where the density really go all the way to 0 actually does form. How do we know that? And so what you want to check is go to numerical simulation. This is one numerical simulation. The color coding is density. And this is the interior of some halo. Blue is basically very low density. Of course, in the numerical simulation, it's never exactly 0. So best you could call this your candidate vortex ring. Yeah. But to really make sure this is a true vortex, what you want to then check is, does the phase wrap around by integer of 2 pi? And so let me take this ring that fortuitously happen to be lie on the x equals 0 plane. So you flip it around and you check basically the winding, which is the next plot. If I flip it around, basically the 2 points where the vortex ring crosses this plane is right here and there. And the phase wrap around in opposite direction by 2 pi in those 2 places. In fact, as far as we know in the simulations, we could not find a winding that's higher. It's always just single winding. Probably by the Taylor series argument that I told you earlier, it's just somewhat unusual, kind of unlikely to have the first order term vanishing also. Okay, so by random chance, these things do form in the nonlinear regime. And in fact, now that you understand this as vortex rings, you might as well just take a simulation and focus on the vortex ring. So let me show you a simulation of that. So I take one of these simulations and just highlight the vortex ring. These are the rings. You can see them at a particular moment in time. These rings move around. They change in size, and they intersect each other. This is one particular very symmetric initial condition so that you can see the ring very nicely. For more realistic initial conditions, the rings look more like this one. They look more messy, but they are still there. There are a few things you want to check about these rings. For example, you want to check to what extent the density goes like the distance square, and these are for basically different rings, distance away from the rings. And roughly speaking, it works. This density square, density goes like distance square. Yes?
Do you have a typical size of the ring, or it's just a random initial condition?
The size seems to be of the order of the Broadly wavelength or smaller. Roughly speaking, you get one ring per the Broadly volume, whatever the Broadly wavelength of the halo happens to be, roughly speaking. That's our understanding. Next, I want to show you a movie that was made by Austin. It's not a numerical solution. Rings intersecting and what happens when they intersect. If you look at this color coding where the real and the imaginary part of the wave function go to 0, where they intersect is where the defect is, which will be highlighted in blue. So you can see we can understand how the rings they can intersect and disappear. And let's say let me just emphasize compared to usual topological defects that are really protected by topology, means they cannot be destroyed or created. Here it's very easy to make them and destroy them. They come and go. If you ask how long do these vortex rings stick around, you use fuzzy dark matter parameters in Milky Way. They stay around for millions of years. They are not there forever, but the time scale is roughly 1 million years. Okay. So additionally, already said roughly one defect per the Broadly volume. You might wonder about the connection with angular momentum. The simulation that I showed you that has this ring, the halo was not even rotating. There's no net angular momentum. So it does not appear you need net angular momentum to have rings. That's comment number one. Number two, it also appears that you do not need rings to have angular momentum. That part is less secure, but we believe so. I think we are still trying to understand that. In other words, these things just formed based on pure chance by the fact that you have waves, superposition thereof, and occasionally you have destructive interference. And that should happen on average 1 per the Broadly volume. Okay. So that's, I think, all I have to say about vortices. And let me switch to a second topic, and it's probably a good way to switch to a second topic by showing you the famous image recently of the Black Hole Event Horizon Telescope. So what I want to consider is the following. Let's think about having a scalar, such as this scalar dark matter, but now in the presence of a black hole. And in particular, I want to talk about the subject that was mentioned a few times already, including Ricardo's talk, the issue of black hole hair. And Ricardo mentioned there was, of course, this classic no-hair theorem by Bekenstein that a black hole cannot have scalar hair. And that theorem can be evaded, if you want, in several ways. And Rico this morning already talked about one of them. I'm going to mention another, and this one is basically by violating boundary condition assumed by Bekenstein. Bekenstein assumed the scalar vanishes at infinity, a fairly reasonable assumption. But suppose you violate that assumption, and it was work done quite a while ago by Ted Jacobson, and he had in mind the following: a massless scalar, but far away, phi has a time profile, linear in time. And then you can very easily show that the scalar field would develop a non-trivial profile around the black hole. In fact, it goes like 1 over r kind of profile. So giving essentially the black hole hair, the scalar charge that you produce this way is proportional to the time derivative of the scalar. At the time of Jacobson, he was interested in cosmologically evolving scalar, so a fairly small time derivative compared to the size of the black hole. So the scalar charge that you get is fairly small. And I should mention a paper by Cliff, who is here. He famously called Jacobson effect the Jacobson miracle hair growth formula. What I will discuss just in the last few minutes is to generalize basically the Jacobson effect if you want. Instead of having a linear time dependence, let's have just an oscillatory time dependence, which is, thank you, which is what you expect if you have scalar dark matter. You have a non-zero mass, so let's say the scalar field is just homogeneous far away, so it oscillates in time. And there ought to be a generalization of the Jacobson effect in this case, and so that's what we calculated. And it's a very simple calculation, so all we did is to solve the good old Klein-Gordon equation in a Schwarzschild background, but just with this boundary condition far away, with a sine basically in time, or cosine in time with frequency m. Let me just make a footnote here. This is, of course, distinct from superradiance, which is an effect that has to do with a rotating black hole. We'll come back to that in a minute. Let me just show you what the solution looks like. So this is, again, solving Gordon and Schwarzschild background. I'm plotting the scalar as a function of R star, basically the same R star in Ricardo's talk. This is the tortoise coordinate. The Schwarzschild radius is set to 1. The mass of the particle is actually also set to 1 here, basically. So the mass, the quantum wavelength matches the horizon size in this particular example. And let me just show you the movie. It goes like this. Very far away, you have oscillation. The oscillation send up waves. It goes into the horizon of the black hole. The horizon is to the far left. 0 here is roughly the light ring in Ricardo's talk. You see the scalar actually amplitude gets magnified. And we work out what is that amplification. The amplification goes like out to the -3/4. So the scalar profile goes like out to -3/4. The amplification stops somewhere basically when you get to the light ring or smaller. Basically it plateaus off. And the wave just travels in the horizon. So to put it in actually the simplest terms, this is nothing other than having dark matter accreting onto the black hole. That's basically all we are doing. This out to the quarter have interesting implications. Let me talk about that. This kind of pile up of scalar, let me also emphasize, it occurs essentially when the mass is of the order of or bigger than Schwarzschild radius. That's basically the particle limit. It turns out even if as long as the mass is bigger than about 10 to the -3 times 1 over Schwarzschild, you would have this out to the 3/4 pile up. So even if you are somewhat in the wave regime, it still works. If you are deep in the wave regime, basically if your mass is less than this, then you stop having this out to the 3/4 pile up. Okay. So comments. The scalar profile depends on the scalar mass in relation to the horizon. So and that's a big if, I don't know of a way to practically do it. If one day we can measure the scalar profile around a black hole, we can measure its mass. You can actually put in numbers and ask how much gravitational back reaction does this pile of the scalar generate. Is really negligible. At best, 10 to the -10 or smaller. So it's a very small, it's some kind of hair, but the gravitational field generated by the hair itself is very small compared to that generated by the black hole. Perhaps more interesting is to think about this as an axion which has lambda 5/4 self-interaction, for example. Phi over f square, there is a range, but it can be somewhere between 10 to the minus 7, 10 to the minus 3. Maybe at the high end, it could be interesting effects. If you think about this as an axion which have self-interaction, and perhaps there are interesting effects that one could think about if this, if you generalize this to a curved black hole, like what Sergei actually has worked on, superradiance. Maybe you're sensitive to this even though it's still a small number. Possibilities, maybe applying this to other scalar theories, which I will not mention here.
These solutions carry like huge amounts of energy, right?
They certainly carry a lot of energy, but still, if you ask what is the curvature generated by this compared to the curvature generated by the black hole, is small. Let's say the Riemann. Yes, that's true. Yes. Okay. So let me end by just mentioning the two topics that I talked about. What is this in superfluid dark matter and black hole hair, and emphasize again my collaborators here. Thank you for your attention.
Okay, any more questions?
Yes. Do you understand why you don't generate a long vortex going from one side of the to the other of the simulation, like you normally in cosmic strings?
Oh, you mean going all the way?
Yeah.
Yeah, I think it probably does have to do with the fact that these are things that just form somewhat randomly by the random superposition, and therefore the coherent size, if you want, is at best about the Broglie wavelength. Of course, you can create such a thing, but it would be probably is not something that naturally occurs from cosmological initial conditions.
This number 10 to the negative 3 to 10 to the negative 7 for phi over f in your scalar hair case.
Yeah.
Where is this coming from, and does this assume a particular choice of, like, you know, gut scale f for m 10 to the negative 22 or something like that?
That's a good point. So here, this phi over f, the f that I assume is the f that I show at the beginning. So it's f that is 10 to the 17 GeV, so fairly high f.
Any more questions?
Yeah, but there you go.
The solution with the oscillating scalar field IPhT is not an exact solution in terms of the metric, right? You're just feeding a Klein-Gordon equation in the,
Yeah, you're saying the galaxy halo has some non-trivial gravitational field.
Yes, and that's given.
That's right. And so therefore that phi is not going to be exactly going like that. It will be inhomogeneous, for example.
No, I'm saying if you consider the back reaction of the metric on the scalar field in the solution.
Yes.
Yes.
No. We assume, so here's what we do. All we did is we solve exactly Schwarzschild background, Klein-Gordon equation, with the boundary condition that phi far away is this cosine in time. That's it. That's all we did, right? But in detail, of course, once you go sufficiently far away, your geometry is not dominated by the black hole anymore. It's dominated by the surrounding galactic halo. The surrounding galactic halo has a gravity potential of the order of 10 to the minus 6 or something like that. So that is going to give you some small modification on the boundary condition far away for sure. Yeah.
Yeah.
Wait, then a follow-up to that question. So if you have a Compton wavelength that's well matched to the black hole's Schwarzschild radius, which is what you want to look at, then the de Broglie wavelength for this field is much longer, and on scales of the de Broglie wavelength, you know,
Nice.
away from right around the black hole,
Yes.
you're probing a region that's not at all dominated by the black hole's potential. So for a realistic, if I
Nice.
look at a realistic dark
Nice.
matter halo that has a black hole at the center,
Yeah.
do you have any sense of how much these results would change?
Yeah, thanks for asking the question. So let's consider this black hole. In particular, this is a very massive 10 to the 9 solar mass black hole. The horizon size, if you turn it into the mass of the scalar, is about 10 to the minus 20 electron volts. So it's somewhat close to this fuzzy dark matter kind of range. And if it's indeed that kind of mass, or maybe even a little bit smaller, what you expect is inside the galactic halo, M87, at the center there should be an object that is like a soliton. So it's a configuration that is basically a configuration of scalar bound together by gravity. And so at least one possibility is for the black hole to be sitting on top of this soliton with a size that is about 10 to the 5 or 10 to the 6 bigger than the black hole. Yeah. I'm not sure if I'm answering the question.
So for example, have you studied in that system what sort of analogous?
Yeah, we estimated these numbers in particular for that system. Numbers. Is in fact for that system. But although it turns out even if you put a 10 solar mass black hole just out somewhere randomly in the Milky Way halo, you get a number that's like 10 to the minus 7. You get this bigger number because of the soliton. The soliton has an enhanced density, and so you get this bigger number. Yeah.
What do you expect the KNHs to do? Because obviously with the M87, that's probably rapidly rotating, right? So
It's probably roughly rotating. So
rapidly rotating. Yeah.
it's probably rotating. M87, as you might know, has a jet. So very likely the jet is coming from the rotation of the black hole. And so certainly there's need to do these calculations for a curved black hole.
Do you have any insight to what kind of things it might change?
Well, it's something briefly mentioned by Sergei. You could have super radiance, for example. So it will be interesting to understand how this black hole hair basically around the black hole, how that might or might not affect super radiance.
Okay. Any more questions? All right. You look like you have an announcement. Yeah. Okay. I'll pass over to you. So thank you again.